Hey everybody, Miss Bodechon here. Today we're going to be looking at our AKS portfolio for 7C. So 7C says, I can plan and carry out investigations to describe how molecular motion relates to thermal energy changes in terms of conduction, convection, and radiation. So we're going to look at each one of those. The first one on your sheet should look something like this. You have your picture of a pan with boiling water and it's over an open flame. It says define conduction, convection, radiation, and then identify which one is which. So we're going to go into the definitions first and look at them. So if you look right here, conduction is a transfer of heat by direct contact, which just means it's actually touching it, okay? And it's a transfer of energy between the particles themselves with direct contact. So as soon as it touches, it will transfer heat from warmer to cooler, whichever one is the warmest, that heat energy will start to transfer to the one that is the cooler one, okay? Convection right here now. Convection is a heat transfer by the movement of molecules within a substance. This takes place within what we call a fluid. So a fluid is going to be a gas or a liquid. So I want you to think about that for a second, what that would look like. So think about like wind currents and ocean currents, right? Like on our planet, wind being made out of air, which is a gas, ocean currents being made out of water, right, which is a liquid. So we have that convection current happening. It's transferring within the molecules themselves, like around in the molecular motion. It always goes again from warmer to cooler. All heat transfers will go from a warmer to cooler area. I just want to keep reiterating that so you really get it, okay? Radiation is last, and radiation is heat transfers through space. So I know that sounds really simple, right? You're like, oh, through space, sure. Well, it can mean a lot of different kinds of space, you guys. It can literally mean like from outer space, like the sunshine. The sun, the heat, the thermal energy from the sun goes across outer space, and it does go through our atmosphere, right, which is no longer outer space because it's in an atmosphere of air, and it can travel through the air as well, right, through molecules and whatnot, and get to us and radiate on us and heat us up and heat up the earth and heat up the oceans and all of that. So we're going to go and we're going to look back at our boiling water and see which one's which to further understand these. So here we go. Easiest one first, conduction. Conduction is, hey, which one is in direct contact, right? Which one has the touching? So the guy right here is holding the pan handle, and the pan handle is super hot. It's over an open flame. So it's super hot. The heat from the handle is moving into the guy's hand, and it's going to start burning because that's so hot, all right? And remember, it goes from warmer to cooler. So the handle is much warmer than the guy's hand is, okay? The next one, convection right here. This is a convection current within the water itself. Remember, convection takes place in a liquid or a gas of fluid, okay? And you can see by these arrows, that's boiling. My water is going around in little circular motions, which we call a current, and it's going warmer to cooler, okay? It's really, really hot at the bottom, which is causing it to be less dense. It goes to the top where it hits the cooler air, it cools down, it becomes more dense, and it goes back down to the bottom where it gets hot, it becomes less dense, and it will make a circular motion, which is called a convection current. All right, that's also how a lava lamp works. Radiation, you can see here in the form of these radiation waves, okay? So these are invisible waves that we can't see, all right? They just drew little squiggly lines to represent them. And what that is it's coming off of the flames. So it's radiating outward, okay? And that's why if you like stick your hands next to an open flame, you'll feel them getting warmer, right? You can warm up your hands because of the radiation from the fire itself is going to be what warms up your fingers, okay? Now, if it's directly over the flame, That's just heat rising, and heat rising is always going to be a form of convection, okay? Heat rising and then cool falling is convection. So I don't want you to confuse the two. So if the heat's coming from the side of the flame, it's going to be radiation. From the top of the flame, it's going to be convection. All right, the next one that you're given is a table for you to fill out. So you need to know the difference between temperature, heat, and thermal energy. These are things that really sound similar until you start to break them down and understand the vocabulary words themselves. So we're going to go into detail about each one. As I'm doing this, go ahead and fill in your chart. Okay. So I'm going to move me around as we do this, okay? So we're first going to look at temperature. So temperature is a measure of average kinetic energy of particles in a substance. It is expressed in Fahrenheit, Celsius, or Kelvin. And you guys know probably that we measure temperature with a thermometer, right? When you get sick, you put a thermometer in your mouth and you see how hot you are. We do this with all different substances, right? It does not vary with the mass of a substance. If we move on over here to thermal energy is the total energy of the particles in a substance. So we're just talking energy now. That's it, okay? It is expressed in joules, like we did for our calculations, finding potential and kinetic energy. It varies with the mass and temperature of a substance, so it's definitely going to change based on those things. If we move even further to heat, heat is a transfer of energy, okay? And I underline that word because it's very important. It's the actual transfer taking place. So heat is not a thing. Heat is a transfer, okay, of energy between objects that are a different temperature. The amount of energy transferred is expressed in joules. So how much energy is given or taken is expressed in joules. And of course, that's going to vary depending on its mass, specific heat capacity, temperature of the substance. I know you don't know what specific heat capacity is yet. Don't worry. We'll learn about that later. Okay. But I want you to know that the heat is actually referring to convection, conduction, and radiation transfer. All right. Okay. The next one, you are asked to look at some different situations and plan investigations. So we're going to look at each one together. The first one, so let me put you right here. The first one says plan an investigation to determine what method of heat transfer would heat up a piece of ice the fastest. Explain what data you would need to collect. So pause your video and think about this for a second, and then come back on and we'll talk. So pause. Okay, now that you're back, let's go ahead and talk. First, we have a piece of ice. We know we have 3 different types of heat transfer: conduction, convection, radiation. We would have to set up a lab to experiment with each one of those and collect data like how big is the piece of ice? We need to make sure they all are the same, right? When we start out, we need to collect how much of the ice has melted at the end in order to determine which was more efficient. How long did it take, right? So these are the kind of things that we would need to look at. A way that you could set it up by doing conduction is getting something that's really, really hot, like at your home, a curling iron. You do not have to do this experiment, okay? This is just hypothetical. We're just talking through this. Get something like a hot poker from your fireplace, or a curling iron, something that heats up really, really hot. Heat up a pan on your stove and then put it on the ice, directly touching it for conduction. See how long it takes to melt, right? For radiation, you can get a heat lamp and you can hook up the heat lamp and just have the light shining from that heat lamp onto the piece of ice, and it can be melting that ice through radiation, okay? And then convection, you could put that ice in something like, I don't know, boiling water or something like that with a convection current, and you could see how long that would take to melt in the actual convection current. All right. The next one, and you guys, those aren't just the only answers. There's tons of answers out there. Those are just an example. Okay. The next one, an aquarium heats the water from the heat lamp. So in this picture, you can see like here's our heat lamp. And the internal heaters close the surface of the water to mimic the sunshine heating the ocean. This creates a warm surface that cools down the deeper you go into the water. Predict the outcome of the thermal energy in the water if the heaters and lamps were to burn out. So this picture is just a really tiny picture to give you the gist. Okay, so we have hot light above it that's supposed to be like the sunshine, right? And the thermal energy comes down and it heats the water in the aquarium tank. So the top of the water is going to be the hottest part. This is the part that's getting the majority of the thermal energy. As we go deeper and deeper into the aquarium water, it's going to get cooler and cooler. That's when the light's on. But what happens when the light goes off? When the light goes off, are we going to maintain that change in temperature? Are we going to maintain having hot at the top and cooler at the bottom? Not for a long time, right? As soon as that goes off, we're going to start coming to what we call equilibrium. And our fish tank is going to start evening out in temperature, all right? So it's going to start mixing. The warmer water is going to go to the cooler water, and it's going to start a little mini convection current within that fish tank. And the warmer will then mix with the cooler, and eventually the entire tank will be the exact same temperature. At that point, it is called equilibrium, okay? And that concludes 7C.